Space is the ultimate mystery box, and every time we think we've got it figured out, it throws something even wilder at us. Picture this. Somewhere out there, there's a planet made of diamond, a cloud of alcohol so massive it could fill 1 trillion cocktail glasses, and a place so cold it makes the depths of space look warm. And that's just the tip of the cosmic iceberg. Today, we're diving into 30 of the weirdest, most mind-bending facts about space exploration that will make you question everything you thought you knew about the universe. From astronauts growing taller in zero gravity to black holes that sing, these aren't your average science class tidbits. Buckle up, because this journey is going to be anything but ordinary. And trust me, by the end, you'll never look at the night sky the same way again. Now let's kick things off with a fact that might make you wish for a quick trip to space. Astronauts actually grow taller while they're up there. Imagine floating in microgravity and suddenly finding your pants are just a little too short. That's exactly what happens to astronauts, and here's why. On Earth, gravity is constantly pressing down on your spine, compressing the discs between your vertebrae like a stack of sponges under weight. But in space, where gravity's pull is practically non-existent, those spinal discs finally get a break. Without that constant pressure, they expand, sometimes adding as much as 2 inches to an astronaut's height. It's like your spine is stretching out after being squished for years, a cosmic version of finally standing up straight after a long flight. But don't start packing your bags for the International Space Station just yet, because this growth spurt doesn't last. Once astronauts return to Earth, gravity goes right back to work, compressing those disks again over a matter of weeks. That means no permanent extra height, just a temporary taste of what it's like to be a little closer to the stars. What's wild is that this isn't just a quirky side effect, it's a serious consideration for space missions. Imagine designing a spacecraft or spacesuit without knowing if the crew might gain an inch or two mid-mission. Scientists even study this phenomenon to prepare for long-term space travel, like future trips to Mars, where astronauts could spend months in microgravity. So while it sounds fun to grow taller, it's also a reminder of how every little detail in space has big consequences down here on Earth. Up next, we're trading height for smell because yes, the moon has a signature scent and it's not what you'd expect. But more on that soon. Now let's take a step into one of the most unexpected sensory experiences in space, because believe it or not, the moon has a smell and it's nothing like fresh cosmic air. When Apollo astronauts returned from their lunar walks and peeled off their helmets inside the landing module, they were hit with a bizarre aroma clinging to their suits. The verdict: moon dust smells like spent gunpowder. Picture this: after hours of bouncing around in low gravity, kicking up powdery lunar soil, the astronauts brought that dust back into their cramped spacecraft. And despite the moon having no atmosphere to carry scents, the moment that fine gray powder mixed with the cabin's oxygen, it released a sharp, metallic tang like the aftermath of fireworks. So why does the moon smell like a battlefield? Scientists have a few theories. One leading idea points to the dust's composition. Lunar soil is packed with tiny shards of glass and minerals like olivine and pyroxene, shattered over billions of years by meteorite impact. These particles are razor-sharp and chemically reactive, especially when exposed to oxygen for the first time. Some researchers think the scent comes from oxidation, a process similar to rusting, as those minerals interact with the moist air inside the spacecraft. Another factor could be solar radiation. Without an atmosphere to shield it, the moon's surface is bombarded by charged particles from the sun, which might alter the chemistry of the dust over time. When astronauts disturb it, they're essentially stirring up particles that have been cooked by space weather, releasing volatile compounds that carry that gunpowder-like punch. Here's the twist: the moon itself doesn't actually smell like anything. In the vacuum of space, there's no air to carry odors. That signature scent only appears when lunar dust meets human-made environments, making it a fleeting, almost ghostly reminder of how alien and oddly familiar space can be. And speaking of eerie cosmic phenomena, our next fact is one that'll make you appreciate the noise around you, because in space, silence isn't just golden. It's absolute. But let's shift gears for a moment, because while space is full of wonders, it's also missing something we take for granted every day: sound. That's right, space is utterly silent. No whooshing starships, no roaring engines, not even a whisper of wind. It's a vacuum, and in a vacuum, sound simply can't exist. Here's why. Sound travels as vibrations through a medium, whether it's air, water, or even solid objects. Think of it like a wave moving through a crowd at a concert, each person nudging the next to pass the energy along. But space is mostly empty, with atoms scattered so far apart that those vibrations have nothing to push against. Without a medium, the waves can't form, and the result is absolute silence. To grasp just how eerie this is, imagine standing in a vacuum chamber here on Earth, a sealed room where all the air has been pumped out. If you shouted inside one, no one would hear you, no matter how loud you were. That's exactly what astronauts experience in space. They could watch a supernova explode in the distance, and it would unfold in perfect silence, like a cosmic fireworks show on mute. This also means that even the most violent events in the universe, colliding galaxies, erupting black holes, or even the birth of stars, happen without a single audible peep. Scientists can see these phenomena through telescopes and translate their energy into radio waves or visual data, but the sound itself is forever lost in the void. Of course, sci-fi movies love to ignore this fact, filling space battles with laser blasts and engine roars for dramatic effect. But the reality is far stranger, a universe bursting with action, yet frozen in perfect, everlasting quiet. And if that leaves you craving a little cosmic noise, don't worry. Our next fact is about a place where the universe sings, just not in a way you'd expect. Now, let's turn our attention to a planet that dances to its own rhythm: Venus. While most planets in our solar system spin counterclockwise like graceful tops, Venus is the rebellious outlier, spinning clockwise in what's called a retrograde rotation. Imagine a ballerina twirling the wrong way in a room full of dancers. It's that kind of cosmic oddity. But Venus's quirks don't stop there. Not only does it spin backward, but it also takes its sweet time doing so. A single rotation on its axis, what we'd call a day, lasts longer than its entire trip around the Sun. That's right, a Venusian day stretches for 243 Earth days, while its year clocks in at just 225 Earth days. So if you lived on Venus, you'd celebrate your birthday before you even finished a single day. What could possibly cause such a bizarre spin? Scientists have a few theories. One leading idea is that Venus suffered a colossal collision in its early history, a planet-sized smack that sent it spinning the wrong way. Another suggests that the tug of the Sun's gravity, combined with its thick, sluggish atmosphere, gradually flipped its rotation over billions of years. Picture a top slowing down, wobbling, and then spinning the opposite direction. That might be Venus's origin story. To put this in perspective, let's compare it to Earth's more conventional behavior. Our planet completes a rotation in 24 hours, giving us predictable sunrises and sunsets. Even Uranus, which rolls on its side like a barrel, still follows the usual counterclockwise spin. But Venus, it's the lone wolf of the solar system, defying the norms with every sluggish turn. And here's another twist: Venus's atmosphere spins much faster than the planet itself. Hurricane-force winds whip around the planet every 4 Earth days, a phenomenon called superrotation. So while the surface crawls, the clouds above race by, a stark contrast that adds to the planet's enigmatic personality. This backward, slow-motion waltz makes Venus a puzzle for astronomers. It's a reminder that even in a universe governed by laws, there's always room for exceptions. planets that march, or in this case, spin to their own beat. Next up, we'll explore a far more intoxicating cosmic wonder, one that might make you wish you had an interstellar cocktail glass. Now, let's take a detour from planetary oddities to something that might sound like the ultimate cosmic happy hour. Drifting through the depths of space near the center of our galaxy, there's a colossal cloud called Sagittarius B2, a gigantic floating cocktail of sorts. This interstellar marvel holds enough ethyl alcohol to fill billions of liquor bottles stretching across light years of space. If you were to pour it out, you'd have enough booze for every person on Earth to drink thousands of liters. But before you start dreaming of interstellar distilleries, let's dive into why this cloud is more fascinating than it is drinkable. So how does a cloud like this even form? Deep in the cold, dense regions of space, molecules like ethyl alcohol, the same type found in your favorite beer or whiskey, can clump together around dust grains. Over millions of years, radiation from nearby stars and the chaotic chemistry of space cause these molecules to bond and multiply, creating vast, sprawling clouds of complex organic compounds. Sagittarius B2 is one of the richest of these molecular clouds, packed not just with alcohol but also with other intriguing ingredients like formaldehyde and even sugar molecules. It's like a cosmic pantry stocked with the building blocks of life, drifting silently in the void. But here's the catch: while the sheer volume of alcohol sounds like a party waiting to happen, you wouldn't want to take a sip. Space is unforgiving, and this cloud is no exception. First, it's incredibly dilute, a few molecules per cubic centimeter, meaning you'd need to process an unimaginable amount of space just to get a single drop. Second, it's mixed with toxic compounds like hydrogen cyanide, which would ruin more than just the flavor. And third, the temperatures in these clouds hover near absolute zero, turning any liquid into a frozen, unreachable mist. What makes Sagittarius B2 truly remarkable, though, isn't just its intoxicating contents, but what it tells us about the universe's ability to create complex molecules. Scientists study clouds like this to understand how organic compounds form in space, compounds that might have eventually seeded life on planets like Earth. It's a humbling reminder that the universe isn't just rocks and fire. It's a sprawling chemical lab brewing the ingredients for existence itself. So while we can't toast with a glass of interstellar whiskey, we can marvel at the fact that somewhere out there, a cloud holds the echoes of chemistry that might one day spark new worlds. Up next, we'll shrink things down to a scale that's almost as hard to grasp: the mind-boggling size of the Sun's core. Shifting our focus from the vastness of interstellar clouds to the heart of our own solar system, let's talk about the Sun, a celestial giant so massive that its core alone could swallow 1,300,000 Earths. Wrap your mind around that for a second. If you lined up our planet end to end, it would take over 1 million of them just to fill the Sun's central furnace. And that's just the core. The entire Sun is so large that it makes up 99.8% of the total mass in our solar system, with everything else, planets, moons, asteroids, barely making a dent. But what's happening inside that unimaginably dense core? It's a non-stop nuclear power plant where temperatures soar to a blistering 15 million degrees Celsius. At these extremes, hydrogen atoms collide with such force that they fuse together, creating helium in a process called nuclear fusion. Every second, the Sun converts 600 million tons of hydrogen into helium, releasing enough energy in that single second to power human civilization for 500,000 years. That's the equivalent of detonating 96 billion 1 megaton nuclear bombs every second. And it's been doing this for 4.6 billion years, with enough fuel left to keep shining for another 5 billion. Now you might wonder how this energy even reaches us. It starts deep in the core, where photons, particles of light, are born from those fusion reactions. But here's the twist: these photons don't zip straight out to space. Instead, they embark on a chaotic 100,000-year journey. bouncing endlessly between atoms in the sun's dense layers. Imagine a pinball machine where the ball takes millennia just to reach the exit. By the time the light escapes the sun's surface, it's only 8 minutes away from warming our faces here on Earth. This relentless fusion is what keeps the sun from collapsing under its own gravity. The outward push of energy balances the inward pull of its immense mass, creating a cosmic tug of war that's lasted billions of years. Without it, the sun would crumple like a deflated balloon. But thanks to this delicate equilibrium, we get just the right amount of heat and light to sustain life on our pale blue dot. So the next time you feel the sun's warmth, remember, you're experiencing energy that began its journey long before humans walked the earth, forged in a furnace so vast it defies comprehension. Up next, we'll trade the sun's fiery heart for a world where time moves in slow motion, Mercury, where a single day lasts longer than most lifetimes. Now, let's journey from the sun's scorching core to its closest planetary neighbor, Mercury, a world where time itself seems to bend in bizarre ways. If you think a Monday on Earth feels endless, wait until you hear this. A single day on Mercury, from one sunrise to the next, lasts a staggering 176 Earth days. That's longer than 2 entire Earth years crammed into just one Mercurian day. How does that even work? Buckle up, because Mercury's timekeeping is a cosmic roller coaster. First, let's untangle the 2 ways a planet measures time. Its rotation, how fast it spins on its axis, and its orbit, how fast it circles the sun. Earth has it easy. We rotate once every 24 hours and orbit the sun every 365 days, making our days and years neatly predictable. But Mercury, it's the solar system's overachiever in weirdness. It rotates painfully slowly, taking 59 Earth days to spin just once. Meanwhile, it zips around the sun at breakneck speed, completing a full orbit in only 88 Earth days. That means a Mercurian year, one trip around the sun, is shorter than its own day. Here's where things get trippy. Because Mercury's rotation and orbit are out of sync, the sun doesn't rise and set like clockwork. Imagine standing on Mercury's surface. The sun would rise, crawl across the sky, then suddenly stop, reverse direction, and dip back below the horizon before rising again hours later. This solar backtracking happens because Mercury's orbit speeds up and slows down due to its elliptical path, while its rotation stays steady. It's like watching a car race where the driver keeps slamming the brakes and hitting the gas, making the sun appear to dance in the sky. But wait, there's more. Mercury's extreme daytime temperatures soar to 430 degrees Celsius, hot enough to melt lead, while nighttime plunges to minus 180 degrees. With such a long day, one side bakes relentlessly while the other freezes in darkness. That's why Mercury's poles, hidden in permanent shadow, might harbor pockets of water ice, a chilling surprise for a planet so close to the sun. So why does Mercury have such a messed up day? Blame the sun's gravity. As the planet whips around its star, tidal forces have slowed its spin over billions of years, locking it into this strange rhythm. It's a reminder that even in space, time isn't universal. It's shaped by gravity, motion, and a dash of celestial chaos. Next up, we'll meet the universe's ultimate speed demons, neutron stars spinning so fast they'd turn a blender into a snail. From the sluggish dance of Mercury's days, let's catapult into the dizzying realm of neutron stars, where the universe's fastest spinners defy all logic. These celestial powerhouses don't just rotate, they whirl with such insane speed that they could outpace a kitchen blender by a factor of millions. Picture this: a neutron star can spin up to 700 times every single second. That means in the time it takes you to blink, this cosmic beacon could complete dozens of full rotations. How does something so mind-bogglingly fast even exist? The answer lies in one of physics' most dramatic transformations, stellar death. When a massive star, at least 8 times heavier than our sun, exhausts its nuclear fuel, it doesn't fade quietly. It explodes in a supernova, blasting away its outer layers and leaving behind an ultra-dense core. Under unimaginable gravitational pressure, protons and electrons are crushed together, merging into neutrons. The result, a neutron star, a stellar corpse so compact that a single sugar cube-sized chunk of it would weigh as much as a mountain on Earth. But here's the wild part. As the star collapses, its rotation accelerates dramatically, just like an ice skater pulling in their arms to spin faster. The numbers are staggering. Take PSRJ 1748, 2446 AD, the current record holder, spinning at an absurd 716 revolutions per second. At its equator, the surface moves at roughly 1/4 the speed of light. That's over 43,000 miles per second, fast enough to circle Earth's equator nearly 1.5 times in the time it takes to snap your fingers. And because neutron stars are so perfectly smooth with surface bumps no taller than a millimeter, their spin remains eerily stable, making them nature's most precise cosmic clocks. But why don't they fly apart? The secret is their insane gravity. A neutron star's gravitational pull is 200 billion times stronger than Earth's, compacting every atom into a swirling neutron superfluid. This density creates a crust 1,000,000 times harder than steel, preventing the star from disintegrating under its own rotation. Some neutron stars, called pulsars, beam radiation like interstellar lighthouses, their jets sweeping past Earth with metronomic regularity. These pulses are so reliable that scientists use them to test Einstein's theory of relativity and even navigate spacecraft. Yet neutron stars aren't just cosmic curiosities, they're gold factories. Collisions between them forge heavy elements like gold, platinum, and uranium in a process called rapid neutron capture, that wedding ring on your finger. Its atoms were likely forged in the fiery aftermath of two neutron stars merging billions of years ago. From their birth in supernova to their role as cosmic alchemists, neutron stars are proof that death in space is anything but quiet. Up next, we'll marvel at a planet where it literally rains diamonds, proof that the universe's luxuries put Earth's riches to shame. Now, let's shift our gaze from the dizzying spins of neutron stars to a celestial gem that would make even the most extravagant jeweler blush, a planet made of diamond. Meet 55 Cancri E, a world so opulent it defies imagination. Orbiting a star 40 light-years away, this exoplanet isn't just rich in carbon. It's likely a glittering sphere of crystallized diamond, larger than Earth and infinitely more luxurious. So how does a diamond planet form? Picture a star system with far more carbon than our own. When the star's protoplanetary disk coalesced, carbon-heavy molecules clumped together under immense heat and pressure, much like how diamonds form deep within Earth's mantle. But here, the scale is cosmic. Scientists believe 55 Cancri E's core is a seething mass of carbon, compressed into diamond over billions of years, with a crust that might resemble a colossal diamond-encrusted shell. The numbers are staggering. This planet's mass is about 8 times Earth's, crammed into a radius twice as wide, making it astonishingly dense. Daytime temperatures soar to nearly 4,700 degrees Fahrenheit, hot enough to vaporize diamonds. Yet its night side, tidally locked to its star, might harbor solid diamond plateaus. And if you're wondering about its value, forget earthly appraisals. Even a tiny fraction of 55 Cancri E's diamond content would surpass our global economy's worth. But here's the catch: mining it is pure science fiction. The planet's surface is a scorching, hostile wasteland, and its gravity would crush any spacecraft instantly. What's just as fascinating as its composition is how it challenges our understanding of planetary diversity. 55 Cancri E isn't just a diamond, it's a laboratory for extreme physics. Its formation hints at carbon-rich star systems where planets could be made of graphite, silicon carbide, or even more exotic materials. Some theorists suggest it might have been a gas giant whose atmosphere was stripped away, leaving behind this crystalline core. Others speculate it could be the remnant of a white dwarf star transformed by gravitational alchemy. But before you dream of interstellar jewel heists, remember, the universe's true treasure isn't the diamond itself, it's the mysteries these discoveries unlock. 55 Cancri forces us to rethink what planets are made of and how they evolve. And speaking of cosmic surprises, our next stop reveals a cosmic blunder that became a triumph. The tale of how humanity fixed the Hubble Space Telescope's blurry vision against all odds. Now, let's turn from dazzling diamond planets to a cosmic comeback story that proves even the brightest minds can make mistakes and fix them. The Hubble Space Telescope, launched in 1990, was meant to revolutionize astronomy by capturing crystal-clear images of the universe. But when its first photos came back, scientists were horrified. Instead of sharp galaxies and crisp star clusters, Hubble's images were fuzzy, like a camera with the wrong prescription glasses. The culprit, a flaw in its primary mirror, one so tiny you'd miss it with the naked eye, but catastrophic for precision optics. The mirror had been polished to the wrong shape, off by just 2 microns, or about 1/50th the width of a human hair. That minuscule error scattered light, leaving Hubble nearly blind to the universe's wonders. The stakes couldn't have been higher. Hubble had cost billions and taken decades to build. Critics called it a boondoggle and NASA a reputation hung in the balance. But rather than give up, engineers devised an audacious fix, a set of corrective lenses akin to glasses for the telescope. In December 1993, the Space Shuttle Endeavour carried a crew of 7 astronauts on a mission that felt like a Hollywood thriller. Over 5 tense spacewalks, they installed the corrective optics package CoStar and swapped Hubble's original camera with a more advanced model. One wrong move could doom the repair, but the team worked with surgical precision. When the first corrected images streamed back, the world gasped. Suddenly, Hubble revealed galaxies in razor-sharp detail, nebulae glowing like cosmic paintings, and planets with staggering clarity. The fix didn't just salvage Hubble, it unleashed its full potential. What's often overlooked is how this near-disaster transformed space science. Hubble's flaw forced engineers to innovate on the fly, leading to breakthroughs in remote diagnostics and modular space repairs. The telescope's upgraded cameras, some added later, would go on to capture iconic images like the Pillars of Creation and the Hubble Deep Field, which peered back over 13 billion years into the universe's infancy. Hubble's redemption also proved the value of human ingenuity in orbit, paving the way for future repair missions to spacecraft like the International Space Station. But perhaps the most poignant lesson here is about imperfection. Hubble's flaw and its triumphant recovery remind us that even our greatest tools aren't infallible, but with perseverance, we can turn failure into discovery. And speaking of cosmic surprises, our next fact dives into a problem closer to home: the growing cloud of space junk circling Earth, a silent threat that could one day trap us on our own planet. Now let's shift our gaze from Hubble's triumph to a looming threat right above our heads, one we can't see but could spell disaster for space exploration. Imagine this: thousands of defunct satellites, spent rocket stages, and even flecks of paint hurtling around Earth at speeds faster than a bullet. This isn't science fiction. It's the growing problem of space junk, and it's turning our planet's orbit into a cosmic minefield. Right now, there are over 27,000 tracked objects larger than a softball circling Earth, and millions more too small to monitor. Every one of them is traveling at roughly 17,500 miles per hour, 10 times faster than a rifle bullet. At those speeds, even a tiny screw can punch through a satellite like a cannonball. In 2009, a single collision between a defunct Russian satellite and an active American one created over 2,000 new pieces of debris, each capable of causing another catastrophic crash. This is the nightmare scenario scientists call Kessler syndrome, a chain reaction of collisions that could blanket Earth in a shroud of shrapnel, making spaceflight impossible for generations. The stakes are terrifyingly real. The International Space Station regularly dodges debris, and astronauts in their capsules have practiced emergency retreats to safer orbits. Satellites that bring us GPS, weather forecasts, and even internet could be wiped out in a cascade of crashes. And here's the twist: space junk doesn't just vanish. In low Earth orbit, where most debris lingers, traces of atmosphere create just enough drag to slow objects down, but it can take decades or even centuries for them to fall and burn up. Meanwhile, we keep adding to the problem. Every rocket launch leaves behind new debris, and companies planning mega constellations of satellites could soon litter orbit with tens of thousands more. But there's hope. Engineers are racing to clean up the mess, testing everything from giant nets and harpoons to lasers that nudge debris into safer paths. The European Space Agency's Clear Space mission aims to launch the first debris removal spacecraft in 2025, targeting a rogue rocket part. Other ideas include satellites with robotic arms or tow trucks that drag junk back to burn up in the atmosphere. Even tiny solutions matter. New satellites are being designed to deorbit themselves at the end of their lives, and rockets now release less leftover debris. The irony: space junk is a problem born of our own success. Every satellite we've launched, every mission we've celebrated, has left a trace. Solving it will take global cooperation, a reminder that exploring the stars means caring for our own backyard first. And speaking of cosmic phenomena closer to home, our next fact takes us to a place where scientists create temperatures colder than the void of space itself. Moving from the chaos of space junk, let's chill out literally with a fact that bends the laws of physics. Believe it or not, the coldest place in the universe isn't in the frozen void between galaxies. It's right here on Earth, or more accurately, just above it, aboard the International Space Station. Inside a device called the Cold Atom Lab, scientists achieve temperatures so low they defy imagination, just a hair above absolute zero, the theoretical limit where all atomic motion stops. To put that in perspective, deep space hovers around -454 degrees Fahrenheit. But in this lab, they've hit temperatures a billion times colder. That's colder than any natural spot in the cosmos. Even the Boomerang Nebula, once considered the universe's icy record holder. How do they pull off this deep freeze? The secret lies in lasers and magnets. Scientists trap atoms in a kind of optical molasses, slowing them down with laser beams until they're nearly motionless. Then they use magnetic fields to evaporate the fastest moving atoms, leaving only the ultra-cold ones behind. The result, a state of matter so bizarre it barely behaves like matter at all, a Bose-Einstein condensate, where atoms lose their individual identities and merge into a single quantum wave. It's like turning a crowd of people into one glowing, synchronized superbeing. Why go to such extremes? These frigid experiments unlock secrets of quantum mechanics, the rules that govern the tiniest particles in existence. By studying atoms in this state, researchers hope to crack mysteries like dark energy, improve atomic clocks for GPS, or even develop quantum computers that could revolutionize technology. And here's the kicker: the microgravity of the ISS is key. On Earth, gravity drags atoms down, ruining the delicate conditions needed. But in orbit, scientists can observe these quantum behaviors for longer, like hitting pause on the universe's fastest dance. The irony is delicious. While we often look to space for extremes, the hottest stars, the densest black holes, this record-breaking cold is something we've cooked up ourselves. It's a reminder that some of the universe's wildest frontiers aren't light years away. They're in labs where humans, armed with ingenuity, push the boundaries of what's possible. And speaking of cosmic contrasts, our next fact takes us from the depths of cold to a world where sunsets paint the sky an otherworldly blue. Now let's trade icy labs for the rusty dunes of Mars, where the sunsets defy everything you know about twilight. Picture this, you're standing on the red planet, watching the sun dip below the horizon, but instead of the warm golds and fiery reds we're used to on Earth, the sky glows a soft, ethereal blue. It's like nature flipped the color palette, and the science behind it is just as mesmerizing. Here's why Mars plays by different rules. On Earth, our thick atmosphere scatters shorter blue wavelengths of sunlight all day, which is why the sky looks blue. At sunset, sunlight has to travel through more atmosphere, and the longer red wavelengths punch through, painting the sky in those iconic hues. But Mars turns that logic upside down. Its atmosphere is just 1% as dense as Earth's, and it's packed with fine iron-rich dust particles. These tiny particles scatter the red light forward, letting it dominate the daytime sky, hence Mars's reddish tint. Meanwhile, the blue light gets scattered in all directions, and at sunset, when sunlight passes through even more dust, that scattered blue becomes the star of the show. The effect is subtle but haunting. NASA rovers have captured it perfectly, a pale blue halo hugging the sun, fading into pinkish twilight. It's a far cry from Earth's dramatic color bursts, but somehow even more alien and beautiful. And there's a twist: Mars's sunsets can vary. During global dust storms, when the air is extra thick with particles, the blue intensifies, almost like the planet is showing off. What does this tell us? Sunsets aren't just pretty, they're cosmic fingerprints. The way light bends and scatters reveals secrets about a planet's air, dust, even its weather patterns. For future Mars colonists, these blue sunsets will be a daily reminder of how different and fragile their new world is. And speaking of fragile, our next fact takes us to a celestial body that's slowly slipping away from Earth's grip. Now, while Mars gifts us with alien blue sunsets, our own moon is quietly staging its slow-motion escape. Here's something that might unsettle your cosmic perspective. Every year, the moon slips about 1.5 inches farther away from Earth. It's not packing its bags overnight, but over millions of years, this tiny drift adds up to a dramatic celestial breakup. So why is our lunar companion pulling away? Blame Earth's oceans. The moon's gravity tugs on our planet, creating tides. But those tides don't just rise and fall, they actually push back on the moon thanks to Earth's rotation. Picture this: Earth spins faster than the moon orbits, so the tidal bulges slightly lead the moon in its path. This gravitational nudge transfers energy to the moon, boosting it into a higher orbit. Meanwhile, Earth's rotation slows down by a whisper, about 1 second every 50,000 years. It's a cosmic trade-off. We lose a bit of spin, and the moon gains a bit of space. This dance has been going on since the moon formed. 4 billion years ago, the moon was 10 times closer to Earth, looming huge in the sky. Back then, a day on Earth lasted just 6 hours, and tides were monstrous walls of water. Over time, as the moon retreated, our days grew longer and tides mellowed. But the drift isn't just a relic of the past, it's reshaping our future. In another 600 million years, the moon will be far enough that total solar eclipses will vanish. No more perfect alignments where the moon precisely covers the sun. It'll appear too small in the sky, leaving only partial or ring of fire eclipses. Here's the poetic twist: the moon can't leave entirely. Once Earth's rotation slows to match the moon's orbit in about 50 billion years, the push and pull will stop, locking both in a gravitational embrace. By then, the sun will have burned out, and the whole neighborhood will look very different. For now, though, the moon's slow retreat is a reminder that even the sky isn't forever. And if you think that's a cosmic plot twist, wait until you hear about Jupiter's shrinking storm. Speaking of cosmic drama, let's turn our attention to Jupiter, where a storm so colossal it could swallow Earth whole is slowly fading into history. The Great Red Spot, Jupiter's most iconic feature, has been raging for at least 400 years, possibly longer. But recent observations reveal this monstrous storm is shrinking, and no one's quite sure what that means for the gas giant's turbulent atmosphere. First, let's unpack the scale of this thing. The Great Red Spot is a hurricane-like storm twice as wide as our entire planet, with winds screaming at 430 miles per hour, 6 times faster than Earth's strongest tornadoes. It spins counterclockwise, a maelstrom of crimson clouds driven by Jupiter's ferocious jet streams. But here's the twist. Measurements from the late 1800s showed the storm stretching 25,000 miles across, wide enough to fit 3 Earths side by side. Today, it's barely half that size, shrinking faster than ever. Scientists are racing to understand why. Some blame Jupiter's chaotic weather patterns, where smaller storms might be chipping away at the Great Red Spot's edges. Others think internal heat or changes in wind speed could be sapping its energy. What's certain is that the storm isn't just getting smaller, it's changing shape. Once a proud oval, it's now more like a squashed circle, with its clouds thinning and fading in places. But here's the real mystery: what happens if it vanishes? The Great Red Spot isn't just a spectacle, it's a window into Jupiter's deep atmosphere. Its stability until now suggested it was anchored by forces far below the cloud tops. If it dissipates entirely, Jupiter's iconic banded appearance could shift, altering how heat and chemicals circulate across the planet. Some researchers even speculate its disappearance might trigger new storms, reshuffling the planet's turbulent weather map. One thing's for sure, Jupiter doesn't do quiet. Even as the Great Red Spot wanes, fresh storms are brewing elsewhere on the planet. In 2019, astronomers spotted a new crimson blemish nicknamed Clyde Spot, suddenly erupting in Jupiter's southern hemisphere. It's a reminder that while one era of storm watching may end, Jupiter's atmosphere is always cooking up something new. And if you think that's wild, just wait until we talk about the solar system's tallest volcano. Now, let's shift our gaze from Jupiter's vanishing storms to something far more permanent, though no less mind-blowing, on our neighboring planet Mars. If you think Earth's Mount Everest is impressive, wait until you meet Olympus Mons, the solar system's tallest volcano. This Martian behemoth stands a staggering 13.6 miles high, nearly 3 times the height of Everest, and spans the width of Arizona. To put that in perspective, if you stood at its base, the summit would vanish into the sky beyond the curve of the planet itself. So how did this colossus form? The secret lies in Mars' unique geology. Unlike Earth, Mars lacks active plate tectonics, meaning its crust doesn't shift or recycle like ours does. On our planet, moving tectonic plates limit how big volcanoes can grow by dragging them away from their magma sources over time. But on Mars, Olympus Mons sat over a single hotspot for billions of years, piling up lava flow after lava flow like a cosmic pancake stack. Its low gravity, just 38% of Earth's, also played a crucial role. With weaker gravity pulling eruptions downward, Martian lava flows spread farther and piled higher, creating gentler slopes that allowed the volcano to grow taller without collapsing under its own weight. And the scale is almost incomprehensible. The caldera, the bowl-shaped depression at Olympus Mons summit, is 50 miles wide, large enough to swallow entire cities. The cliff-like edges around its base, where ancient lava flows met the surrounding plains, tower up to 5 miles high. Yet despite its size, you wouldn't see a dramatic eruption if you visited. Olympus Mons is likely dormant now, its last eruptions occurring tens of millions of years ago. But its sheer presence hints at Mars' fiery past, when the planet crackled with volcanic activity far more intense than anything on Earth today. What's truly fascinating is how Olympus Mons reshapes our understanding of planetary evolution. On Earth, erosion and tectonic activity erase geological features over time. But Mars, with its thin atmosphere and frozen geology, preserves its history like a museum. Olympus Mons isn't just a record-breaking volcano. It's a time capsule offering clues about Mars' molten interior, lost magnetic field, and even why the planet's climate changed so drastically. And if that hasn't blown your mind yet, just wait until we talk about Saturn's disappearing rings. moving from the ancient slopes of Olympus Mons, let's turn our attention to a celestial wonder that's surprisingly short-lived: Saturn's dazzling rings. These iconic bands of ice and rock, often seen as timeless symbols of the cosmos, are actually cosmic newcomers. Believe it or not, Saturn's rings didn't exist when dinosaurs roamed Earth. They formed a mere 100 million years ago, and in another 300 million years they'll be gone. So how did these rings come to be? The leading theory suggests a dramatic cosmic collision. A moon, or perhaps a passing comet, strayed too close to Saturn and was torn apart by the planet's immense gravity. The debris from this violent event didn't fall to the surface or drift away. Instead, it was captured in orbit, forming the stunning rings we see today. Unlike the static, unchanging appearance they give off from afar, the rings are incredibly dynamic. Billions of ice particles, ranging from dust-sized grains to chunks as large as houses, constantly collide, break apart, and reform in a delicate dance around the planet. But why are the rings doomed? Saturn's gravity isn't just holding them in place, it's also pulling them downward. A steady rain of ring material, dubbed ring rain, falls into the planet's atmosphere every second. Scientists estimate this process drains enough water to fill an Olympic-sized swimming pool every half hour. Over millions of years, this slow but relentless erosion will consume the rings entirely. In fact, measurements from the Cassini spacecraft revealed the rings are losing mass faster than previously thought, meaning their demise might come even sooner. What makes this even more fascinating is the timing. In the grand scale of the solar system's 4.5 billion-year history, Saturn's rings are a fleeting spectacle. They appeared long after the planets formed, and they'll vanish long before the Sun begins its death throes. We're living in a rare window where Saturn wears its crown, a privilege not shared by early dinosaurs or future civilizations. And here's the kicker: Saturn isn't the only ringed planet, but its rings are by far the brightest and most extensive. Jupiter, Uranus, and Neptune have faint, dusty rings of their own, but none compare to Saturn's grandeur. This raises a tantalizing question: could these other planets have once had glorious rings like Saturn's, only to lose them over time? The fate of Saturn's rings hints that ring systems might be common but ephemeral stages in a planet's life. So the next time you gaze at Saturn through a telescope, remember, you're witnessing a cosmic masterpiece on borrowed time. And speaking of time, let's talk about a world where a single year lasts longer than most human lifetimes: Pluto. Now let's journey to the edge of our solar system, where time moves at a glacial pace. Pluto, the tiny world that lost its planetary status but gained our fascination, holds a surprising record. Its year is staggeringly long. While Earth zips around the Sun in 365 days, Pluto takes a whopping 248 Earth years to complete just one orbit. To put that into perspective, the last time Pluto was in the same position it is today, the United States didn't exist, Mozart hadn't been born, and the Industrial Revolution was still centuries away. Pluto's marathon year isn't just a quirky fact, it's a consequence of its enormous elliptical orbit. At its closest, Pluto swings within about 3 billion miles of the Sun, but at its farthest it drifts nearly 5 billion miles away. That's like traveling from New York to Los Angeles over 2 million times. And because it's so far from the Sun's warmth, Pluto's seasons are extreme. A single season there can last more than 60 Earth years. Imagine a winter so long, your great-grandchildren would be born before spring finally arrived. What's even wilder is how this timeline stacks up against human history. If you were born on Pluto the same year Shakespeare wrote Hamlet, you'd only now be celebrating your first birthday. The Wright brothers' first flight, that would have happened less than halfway through your Pluto year childhood. And if you lived a full Plutonian century, you'd have witnessed less than half of one orbit around the Sun. Pop culture offers another way to grasp this timescale. The last time Pluto completed an orbit, the world had never heard of electricity, let alone smartphones. If you started streaming your favorite TV show when Pluto began its current year, you'd have to watch it non-stop for over 2 million episodes before the planet reached the same point again. Even the iconic Star Wars franchise, spanning decades of films, would feel like a fleeting moment in Plutonian time. But Pluto's slow dance isn't just a curiosity, it affects everything on its icy surface. Sunlight there is so faint you could hold a midnight picnic at noon and barely need sunglasses. The thin atmosphere, made mostly of nitrogen, freezes and falls as snow for decades at a time. And because a day on Pluto lasts 6.5 Earth days, you'd need serious patience just to watch a sunrise. Here's the kicker: Pluto hasn't even completed one full orbit since its discovery in 1930. By the time it finally does, in the year 2178, humanity might be exploring stars beyond our solar system. So while Pluto may be small and distant, its leisurely pace reminds us just how vast and varied time can be across the cosmos. And speaking of cosmic extremes, let's zoom toward a place where speed defies imagination: the dizzying spin of neutron stars. Now let's shift from the frozen, slow-moving edges of the solar system to the bustling speedway just above our heads, the International Space Station. Hurtling around Earth at a jaw-dropping 17,500 miles per hour, the ISS is the ultimate high-speed commute. To put that into perspective, that's about 10 times faster than a rifle bullet, or roughly the speed it would take to travel from New York to Los Angeles in under 10 minutes. At this velocity, astronauts on board experience something truly surreal: 16 sunrises and sunsets every single day. How does this work? Well, the ISS orbits Earth once every 90 minutes, meaning it completes a full lap around our planet 16 times in 24 hours. That's a sunrise roughly every 45 minutes, turning the concept of a day completely upside down. Imagine trying to stick to a sleep schedule when the sun keeps popping up like a cosmic jack-in-the-box. To cope, astronauts follow a strict schedule based on Greenwich Mean Time, with designated nighttime periods where they dim the lights and pretend it's dark outside, even as the sun blazes past their windows again and again. But speed isn't just about dizzying views, it's a matter of survival. The ISS travels at this breakneck pace to maintain a stable orbit, balancing the pull of Earth's gravity with the forward momentum that keeps it from crashing down. If it slowed even slightly, it would begin a deadly descent, and here's where the engineering marvels kick in. The station is equipped with gyroscopes and thrusters that make constant, tiny adjustments to its position, dodging space debris and staying on course. Even a fleck of paint traveling at orbital speeds could punch a hole through the hull, so teams on Earth monitor thousands of potential hazards around the clock. Safety doesn't stop there. The ISS is built like a nested Russian doll, with multiple layers of shielding to protect against micrometeorites and radiation. Its modules are pressurized separately, so if one compartment is breached, the others can seal off instantly. Astronauts even train for the worst-case scenario, a sudden depressurization, by practicing emergency drills where they must evacuate to the attached Soyuz spacecraft within minutes. And let's not forget the human side of this high-speed life. Simple tasks become feats of ingenuity. Drinking coffee that requires a special zero-gravity cup to keep liquid from floating away. Going for a jog, astronauts strap themselves to a treadmill with bungee cords to simulate the feeling of running on Earth. Even sleeping requires Velcro straps to stop them from drifting into the walls. But perhaps the most mind-bending fact of all is this: the ISS has been continuously inhabited for over 2 decades, a testament to human collaboration across borders. It's a symbol of what we can achieve when we work together, hurtling through the void at unimaginable speeds, yet keeping the fragile flame of life burning in the darkness. And speaking of darkness, let's turn our attention to a place where light itself bends to the will of gravity, the eerie realm of black holes. Now, let's venture from the high-speed life aboard the ISS to a microscopic menace that could pose a big problem for future space explorers: supercharged bacteria. You might think space is a sterile environment, but the reality is far more surprising. Studies have shown that some bacteria, including notorious superbugs like MRSA, don't just survive in microgravity, they thrive, becoming stronger and more resilient than their Earth-bound counterparts. So, what's happening here? On Earth, gravity plays a key role in how bacteria grow and behave. Fluids around them settle, and nutrients distribute predictably. But in space, the absence of gravity creates a chaotic, free-floating environment. Bacteria form thicker, more resistant biofilms, slimy layers that cling to surfaces and shield them from antibiotics. Researchers have observed this with MRSA, a bacterium already notorious for its resistance to treatment. In microgravity, its biofilm structures become more complex, making it even harder to kill. This isn't just a lab curiosity, it's a real concern for long-term missions. Imagine a tiny cut on an astronaut's hand getting infected with a supercharged strain of bacteria. On Earth, antibiotics might clear it up, but in space, the same treatment could fail, turning a minor injury into a life-threatening crisis. NASA and other agencies are deeply invested in studying this phenomenon, running experiments on the ISS to understand how and why bacteria mutate in space. One theory suggests that the stress of microgravity triggers genetic changes in bacteria, activating survival mechanisms that also happen to boost their resistance. Another angle points to the way fluids behave in space, creating ideal conditions for biofilms to flourish. Whatever the cause, the implications are clear. If we're serious about sending humans to Mars or beyond, we'll need new strategies to keep these microscopic hitchhikers in check. Scientists are exploring everything from advanced antimicrobial coatings for spacecraft interiors to novel drug formulations that can outsmart space-adapted bacteria. Some even propose using probiotics, beneficial bacteria, to crowd out harmful ones. It's a race against time, as every year spent in space brings new data and new challenges. Here's the twist: this research isn't just helping astronauts. Findings from space-based studies are already informing how we fight superbugs on Earth, where antibiotic resistance is a growing crisis. By understanding how bacteria evolve in extreme environments, we're uncovering clues to defeat them everywhere. So, while these tiny organisms might be invisible to the naked eye, their impact on space exploration and medicine as a whole is anything but small. And as we push further into the cosmos, we'll need to stay one step ahead of these microscopic adversaries. Speaking of cosmic challenges, let's turn our gaze to a planet that rolls through space like a barrel: Uranus, with its bizarre sideways spin. Now, let's take a cosmic detour to one of the solar system's most peculiar planets, Uranus. Picture this: while most planets spin like tops as they orbit the Sun, Uranus rolls through space like a barrel, tipped over on its side with an extreme 98-degree axial tilt. That means its north pole points almost directly at the Sun during part of its orbit, creating some of the most bizarre seasonal patterns you could imagine. Here's what makes Uranus so unique. Unlike Earth, where seasons change gradually as our planet tilts slightly toward or away from the Sun, Uranus experiences seasons that are downright extreme. For about 21 Earth years, one pole is bathed in continuous sunlight, while the other plunges into total darkness. Then, as it continues its 84 Earth-year orbit, the roles reverse. Imagine living in a place where the sun doesn't rise for decades, only to return and hang in the sky without setting for another 2 decades. That's the reality on this icy giant. Scientists have a few theories about how Uranus ended up in this sideways state. The leading idea suggests a colossal collision billions of years ago, when a massive object, possibly an early planet or large moon, smacked into Uranus with enough force to knock it off its original axis. Another theory proposes gravitational tugs from neighboring planets over time, slowly tilting it sideways. Whatever the cause, the result is a world that defies the norms of our solar system. The tilt doesn't just affect seasons, it also warps Uranus's magnetic field. Unlike Earth's relatively aligned magnetic poles, Uranus's magnetic field is off-kilter, tilted by about 60 degrees from its rotational axis and offset from the planet's center. This creates a magnetosphere that wobbles wildly as the planet rotates, adding another layer of strangeness to this already enigmatic world. Even its weather is odd. Despite being an ice giant, Uranus boasts some of the coldest temperatures in the solar system, dipping below -370 degrees Fahrenheit. Yet, when Voyager 2 flew by in 1986, it spotted bland, featureless cloud tops, nothing like the vibrant storms of Jupiter or Saturn. More recent observations, though, have revealed subtle bands and occasional storms, hinting that Uranus might have more atmospheric drama than we once thought. One thing's for sure, Uranus keeps astronomers guessing. Its oddball behavior challenges our understanding of planetary formation and evolution, making it a prime target for future missions. Proposals like the Uranus Orbiter and Probe aim to unlock its secrets, from the composition of its icy mantle to the mysteries of its tilted dynamo. So, while Uranus might not get as much attention as its showier planetary neighbors, its peculiarities make it a cosmic gem. Whether it's the decades-long seasons, the lopsided magnetic field, or the lingering question of how it got so sideways, this planet proves that in space, normal is relative. And speaking of cosmic oddities, let's shift our gaze to an even bigger spectacle, the Andromeda Galaxy, on a collision course with our own Milky Way. Now, let's zoom out from our solar system and gaze into the far future where two cosmic giants are set for an epic encounter. The Andromeda Galaxy, our nearest spiral neighbor, is hurtling toward the Milky Way at an astonishing speed of around 250,000 miles per hour. But don't panic, this celestial dance won't happen for another 4 billion years. When it does, it'll be one of the most spectacular events in the history of our universe. Here's the fascinating part. Galaxies colliding isn't the chaotic smash-up you might imagine. Space is vast, and the distances between stars are so enormous that actual stellar collisions are incredibly rare. Instead, the Milky Way and Andromeda will perform a gravitational tango, slowly merging over billions of years. Picture two swirling clouds of stars passing through each other, their shapes distorting as gravity pulls them closer. Eventually, they'll settle into a single, massive elliptical galaxy, often nicknamed Milkdromeda by astronomers. What would this look like from Earth? If humanity is still around, future skywatchers would witness Andromeda growing larger and brighter in the night sky. Right now, it's a faint smudge visible to the naked eye under dark skies, but as it approaches, its spiral arms would become more distinct. During the closest pass, the night sky might be filled with a breathtaking display of new stars, gas clouds, and tidal streams, a celestial light show unlike anything we've ever seen. But here's the twist, our solar system might not even be in the Milky Way by then. Recent research suggests the Sun could be flung into a new orbit, possibly even ending up in Andromeda's territory during the merger. Yet, the odds of our planet or any star system being disrupted are vanishingly small. The real drama will unfold in the galaxy's centers, where their supermassive black holes will eventually spiral toward each other, emitting ripples of gravitational waves before merging into one colossal black hole. This cosmic event isn't just science fiction, it's a reminder of how dynamic our universe truly is. Galaxies collide far more often than you might think. In fact, the Milky Way has already absorbed smaller galaxies in the past, like the Gaia-Enceladus galaxy, which it devoured billions of years ago. Andromeda itself shows signs of past mergers, with streams of stars hinting at a violent history. While 4 billion years is an almost unimaginable time frame, studying galactic collisions helps us understand the life cycles of galaxies. Telescopes like Hubble and JWST have captured stunning images of other merging galaxies, giving us a preview of our own distant fate. So, while we won't be around to see Andromeda take shape, the universe will keep evolving in ways that still humble and astonish us. And speaking of cosmic wonders, let's turn to something a little closer to home, or rather, closer to the astronauts who have experienced space firsthand. Did you know that in zero gravity, tears don't fall? They form floating bubbles around your eyes, turning even the most emotional moments into something surreal. Now, let's shift from the grand scale of colliding galaxies to something far more intimate yet just as strange. When it comes to life in space, imagine you're an astronaut floating hundreds of miles above Earth, overwhelmed by the sight of our planet or maybe just missing home. You feel tears welling up, but here's the twist. In zero gravity, those tears don't fall. Instead, they cling to your eyes, forming watery bubbles that just sit there, making even the most heartfelt moments look like something out of a sci-fi movie. This bizarre phenomenon happens because gravity isn't pulling the tears downward like it does on Earth. Without that force, surface tension, the same thing that makes water bead up on a leaf, keeps the tears gathered into glistening spheres. At first, it might just feel like your eyes are extra watery, but if enough tears build up, they can merge into a single, floating bubble that eventually detaches and drifts away. Astronauts have described wiping their eyes only to send a tear bubble floating off into the cabin, where it might hover until it hits a wall or gets caught in airflow. But here's where it gets even weirder. If you cry too much in space, those tears can start to cause problems. On Earth, tears drain naturally through tiny ducts in your eyes, but in microgravity, they don't. That means excessive crying can lead to a buildup of fluid, making your eyes sting or even temporarily blur your vision. Some astronauts report that the sensation feels like having allergies. Your eyes get puffy, but the tears just won't go away. And it's not just tears, other bodily fluids act strangely in space too. Sweat doesn't drip, it clings to your skin until it evaporates or gets wiped away. Even blood behaves differently, pooling in the upper body because there's no gravity to pull it downward, which is why astronauts often look puffy-faced in videos. But tears are uniquely surreal because they're so tied to emotion. Imagine watching a heartfelt message from your family, only to have your own tears floating in front of your face like tiny liquid lenses. This quirk of spaceflight isn't just a curiosity, it's a reminder of how deeply gravity shapes every aspect of our biology. From the way we cry to how our blood circulates, our bodies evolved for Earth's pull. That's why astronauts train for years to adapt to these changes, and why engineers design everything from space toilets to exercise machines to compensate for what gravity once handled. So the next time you wipe away a tear, take a second to appreciate gravity's unseen role in that simple act. And if you ever find yourself in space, maybe save the big cries for your return to Earth, unless you're okay with your sadness literally floating around you. Speaking of things we take for granted on Earth, did you know there's water ice hiding in the shadows of the moon? It's not just a desert up there. Let's explore where it's hiding and why it matters for the future of space exploration. Now, let's turn our attention from the watery oddities of human tears in space to something far more practical: water where you'd least expect it. Hidden in the permanently shadowed craters at the moon's poles, scientists have confirmed the existence of water ice, a discovery that could revolutionize how we explore the cosmos. For decades, the moon was thought to be a barren, bone-dry world, but recent missions like NASA's a Lunar Reconnaissance Orbiter and India's Chandrayaan-1 have shattered that assumption. These spacecraft detected unmistakable signs of water ice lurking in craters where sunlight never reaches, where temperatures plummet to -400 degrees Fahrenheit. These shadowy pockets act like cosmic freezers, preserving ice that may have been deposited by comet impacts billions of years ago. So why does this matter? Water isn't just for drinking, it's a potential gold mine for future lunar colonies. Split it into hydrogen and oxygen, and you've got breathable air for astronauts and rocket fuel to power missions deeper into space. Imagine a lunar outpost where ice mined from the moon's surface is converted into fuel, turning our celestial neighbor into a cosmic gas station. This could slash the cost of space travel, since launching water from Earth's gravity well is incredibly expensive. Every gallon mined on the moon is one less gallon we'd need to haul from home. But the ice isn't just sitting there in easy-to-reach sheets. It's mixed with lunar soil, meaning extracting it will require clever technology. Proposals range from solar-powered rovers that bake the soil to release water vapor, to giant mirrors that redirect sunlight into craters to melt the ice. Some scientists even envision robotic drills capable of mining ice from depths of several feet. The presence of water also raises tantalizing questions about the moon's history. Could these icy deposits hold clues about how water arrived in our solar system? Some researchers speculate that the same comets that delivered water to the moon may have also seeded Earth's oceans. If so, studying lunar ice could help us unravel the story of how our own planet became habitable. Looking ahead, NASA Artemis program aims to land astronauts near the lunar South Pole by 2026, specifically targeting these icy regions. If successful, it could mark the beginning of a sustained human presence on the moon, fueled by the resources already waiting there. From floating tear bubbles to hidden ice reserves, space never fails to surprise us. And speaking of surprises, did you know a single spoonful of a neutron star would weigh as much as a mountain? That's a density so extreme it bends the imagination. Let's unpack that next. Now, shifting our gaze from the moon's hidden ice to the far more extreme realms of the cosmos, let's grapple with something almost unfathomable: the mind-bending density of neutron stars. Picture this: a single spoonful of material from one of these stellar remnants would weigh as much as Mount Everest. That's not science fiction. It's the staggering reality of physics pushed to its limits. Neutron stars are the collapsed cores of massive stars that exploded as supernova. What's left behind is so dense that protons and electrons are crushed together, forming a sea of neutrons packed tighter than atoms in a diamond. To put it in perspective, if you could scoop a teaspoon of this material, it would tip the scales at around 1 billion tons. That's like squeezing the mass of every car on Earth into something the size of a sugar cube. How does something so unimaginably dense even exist? It all comes down to gravity's ruthless power. When a star many times heavier than our Sun dies, its core collapses under its own weight. The force is so intense that it overcomes the repulsion between atomic particles, smashing them into a neutron-rich soup. The result is an object just 12 miles wide, smaller than some cities, but with a gravitational pull 100 billion times stronger than Earth. Step too close and the tidal forces would stretch you into a strand of atoms before you even realized what was happening. But neutron stars aren't just cosmic curiosities, they're also extreme laboratories. Their intense gravity warps space-time so severely that they can serve as natural tests for Einstein's theory of relativity. Some, called pulsars, spin hundreds of times per second, sending out beams of radiation like interstellar lighthouses. Others, known as magnetars, have magnetic fields so powerful they could wipe data from every credit card on Earth from halfway across the galaxy. What's truly humbling is that these monstrous objects are everywhere. The Milky Way alone likely harbors hundreds of millions of neutron stars, remnants of stellar lives that ended in spectacular fashion. And while we'll never visit one, getting within 1,000 miles would be lethal. Studying them from afar helps us understand the universe's most violent and energetic processes. From the moon's icy caches to the crushing weight of a neutron star, space constantly reminds us that reality outshines even our wildest imaginations. And speaking of cosmic extremes, did you know black holes can actually sing? That's a tune you won't forget. Let's explore that next. Now, let's take a step back from the dizzying extremes of neutron stars and celebrate a quieter but no less extraordinary achievement. Humanity's robotic ambassadors have now visited every single planet in our solar system. That's right, from the scorching surface of Mercury to the icy plains of Pluto, our spacecraft have boldly gone where no human has ever set foot. It all began in the 1960s with Mariner 2, the first spacecraft to successfully fly by Venus in 1962. That mission cracked open the door, proving we could send machines across millions of miles to study other worlds. But the real game changer came in the 70s with the twin Voyager probes. These intrepid explorers performed the ultimate grand tour, swinging past Jupiter, Saturn, Uranus, and Neptune, revealing storms bigger than Earth and moons with erupting geysers. Voyager 1 even gave us the iconic pale blue dot image, a humbling reminder of our tiny place in the cosmos. Then came the 90s and 2000s when our reach extended even further. The Galileo probe spent 8 years orbiting Jupiter, diving into its violent storms, while Cassini spent 13 glorious years unraveling Saturn's mysteries, from its ethereal rings to the methane lakes of its moon Titan. Meanwhile, Little Messenger became the first to orbit Mercury, enduring temperatures hot enough to melt lead just to map its cratered surface. And who could forget New Horizons? In 2015, this plucky spacecraft raced past Pluto after a 9-year journey, capturing breathtaking images of frozen mountains and heart-shaped glaciers on a world once thought to be little more than a frozen rock. It didn't stop there. It went on to explore Arakoth, a primordial relic from the solar system's birth, shaped like a cosmic snowman. Even the outermost gas giants weren't left out. Though Uranus and Neptune have only had fleeting visits from Voyager 2, the data it sent back still fuels discoveries today. Now, missions like Juno at Jupiter and Perseverance on Mars continue the legacy, proving that robotic explorers are our eyes and hands in the cosmos. What's incredible is how much these missions have rewritten the textbooks. Before Voyager, Jupiter's moon Io was just a dot. Now we know it's the most volcanically active place in the solar system. Before Cassini, Saturn's rings were simple bands. Now we see them as dynamic, ever-changing structures. Every flyby, every orbit has peeled back another layer of wonder, showing us that every planet has a story to tell. And speaking of stories, did you know the universe might be hiding one of its biggest secrets in plain sight? Up next, we'll explore the mind-bending idea that our entire reality could be a cosmic hologram. Now, let's turn our attention to something that happens every single day, yet feels almost impossible when you think about it. The sunlight warming your face isn't instant. It's a tiny time traveler. Here's the wild part: when you look up at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. That's because light, as fast as it is, still takes time to cross the vast emptiness of space. To put this into perspective, imagine shouting to a friend across a football field. There's a delay between when you speak and when they hear you because sound has to physically travel through the air. Light works the same way, except it's so fast, about 186,000 miles per second, that we usually don't notice the lag. But space is so mind-bogglingly huge that even light can't cheat the clock. The sun sits an average of 93 million miles away from Earth, and at light speed, that journey takes roughly 8 minutes. This means if the sun suddenly vanished, poof, we wouldn't know for those full 8 minutes. The sky would still be bright, the planets would keep orbiting an empty spot, and Earth would stay warm until that last glimmer of light finally reached us. It's a haunting thought, but it also reveals something beautiful about the universe. Every time you feel sunlight, you're literally touching the past. And this delay isn't just a sun-Earth quirk. It scales with distance. The farther something is, the older the light we're seeing. Take Jupiter. When it's closest to us, the light from its clouds takes about 35 minutes to arrive. For Pluto, that light's over 4 hours old by the time it reaches your eyes. Even our galaxy, the Milky Way, is a patchwork of different time periods. The stars in Orion's belt are so far apart that some of their light left centuries before others. This time lag is why astronomers are essentially historians. When we peer at distant galaxies billions of light years away, we're seeing them as they were billions of years ago, snapshots from the universe's childhood. It's like having a cosmic time machine built into the very fabric of reality. So next time you squint at the sun, remember, you're not just seeing a star. You're seeing a message from 8 minutes in the past carried across space by the universe's fastest traveler. And speaking of messages, imagine if space itself could talk. Up next, we'll listen to the eerie song of a black hole. But if you think the concept of light as a time traveler is mind-bending, wait until you hear this. The number of stars in the observable universe is so vast, it makes every grain of sand on Earth look like a drop in the ocean. Let that sink in for a moment. Every beach you've ever walked on, every desert stretching to the horizon, every speck of sand in every corner of our planet combined, they still don't come close to the number of stars twinkling out there. Scientists estimate there are roughly 100 billion stars in our Milky Way galaxy alone. That's already an unimaginable number, but here's where it gets wild. The observable universe contains at least 2 trillion galaxies. If each of those galaxies has even half as many stars as ours, we're looking at a number so large it defies everyday understanding. To put it in perspective, there are about 7.5 quintillion grains of sand on all Earth's beaches and deserts. That's a 7 followed by 18 zeros. But the estimated number of stars, around 1 followed by 24 zeros, that's 1,000,000 times more stars than grains of sand. Now, imagine holding a single grain of sand between your fingers. That tiny speck represents an entire galaxy's worth of stars in this cosmic comparison. It's a humbling reminder of just how small we are in the grand scheme of things. Yet, there's something oddly comforting about it too. Every star we see is a sun, potentially with its own planets, maybe even life. The universe isn't just big, it's overflowing with possibilities. And here's another twist: we're only talking about the observable universe. The actual cosmos might be infinitely larger, but we'll never know for sure because light from those unreachable regions hasn't had time to reach us yet. It's like standing on a shore, staring at an ocean where the horizon never ends. So next time you're at the beach, scoop up a handful of sand and let it trickle through your fingers. Each grain is a reminder of the unimaginable scale above us. And if that doesn't make you feel both tiny and wonderfully connected to the cosmos, just wait, because up next, we're turning up the volume on one of space's most haunting melodies, the song of a black hole. But before we dive into the cosmic concert of black holes, let's take a moment to appreciate just how bizarre this phenomenon really is. Picture the universe's most destructive force, a region of space-time where gravity is so intense, not even light can escape, and now imagine it singing. It sounds like science fiction, but thanks to NASA's Chandra X-ray Observatory, we've literally heard the sound of a black hole. Here's how it works. In 2003, astronomers detected pressure waves rippling through the hot gas surrounding a supermassive black hole in the Perseus galaxy cluster, 250 million light-years away. These waves were essentially vibrations in the fabric of space itself, caused by the black hole's gravitational influence. But here's the catch: space is a vacuum, so sound as we know it can't travel. Instead, these waves were translated into a note 57 octaves below middle C, a frequency far too low for human ears to hear. NASA shifted the pitch up by an astonishing 57 octaves and amplified it, giving us a ghostly hum that's been called the black hole's song. The result, a single haunting note that lingers like a cosmic whisper. It's not a melody or a tune, but a deep, resonant tone that seems to reverberate through your bones. Scientists describe it as the lowest note in the universe, a B-flat more than 1,000,000 billion times deeper than the deepest sound humans can perceive. And here's the mind-blowing part: that note has been echoing through space for about 2 billion years. But why does a black hole sing at all? Think of it like ripples in a pond. The black hole's immense gravity churns the surrounding gas, creating waves that propagate outward. These waves compress and heat the gas, producing X-rays that Chandra can detect. By sonifying that data, turning it into sound, we get a glimpse of the black hole's hidden voice. It's a reminder that even the most violent cosmic events can leave behind something oddly beautiful. Now, if you're expecting a symphony, you might be disappointed. This isn't music in the traditional sense, but that single note carries profound meaning. It's a direct signal from one of the universe's most enigmatic objects, a way for us to hear the invisible. And in a way, it's poetic. A black hole, often depicted as a silent void, actually has a voice. It's just waiting for us to listen. So next time you gaze at the night sky, remember, the cosmos isn't just a visual spectacle. It's a chorus of unseen vibrations, a symphony of forces we're only beginning to understand. And as we uncover more of these cosmic secrets, who knows what other melodies might be waiting in the dark? Up next, we're tackling one of the most mind-bending theories of all, the idea that our universe might not be what it seems. Is reality just a hologram? Let's find out. Now, shifting our gaze from the haunting melodies of black holes, let's venture into a theory that challenges everything we think we know about reality itself. What if I told you the universe, the stars, the planets, even you and me, might not be as three-dimensional as it seems? Buckle up, because we're diving into one of the most radical ideas in modern physics, the holographic principle. At its core, this theory suggests that our seemingly solid, three-dimensional universe could actually be a projection of information encoded on a two-dimensional surface, like a cosmic version of a hologram. Imagine a movie screen displaying a 3D image, even though the screen itself is flat. The holographic principle proposes that the universe works in a similar way, with all the information about our 3D reality stored on a distant two-dimensional boundary. This mind-bending idea emerged from the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the entropy, or disorder, of a black hole isn't proportional to its volume as you'd expect, but to its surface area. Later, Stephen Hawking confirmed this with his work on black hole radiation. This odd connection between surface and volume hinted at something deeper. Perhaps the universe records information at its edges, not within its bulk. Fast forward to the 1990s, when physicist Gerard T. Hooft and later Leonard Susskind formalized this idea into the holographic principle. They argued that the maximum amount of information a region of space can contain isn't determined by its volume but by its surface area. In other words, everything happening inside a given space could, in theory, be described by data painted on its outer boundary. But how could this possibly work? Think of it like a video game. The graphics on your screen appear three-dimensional, but they're ultimately generated by code, a flat, two-dimensional set of instructions. Similarly, the holographic principle suggests that the universe's 3D richness might arise from underlying 2D data. Even stranger, this could mean that time and space as we experience them aren't fundamental but emergent properties, like the illusion of depth in a hologram. Now, before you start questioning whether your coffee cup is real, let's be clear, this isn't saying the universe is an illusion. Rather, it's a radical rethinking of how information structures reality. And while the math checks out in theoretical models like string theory's ADS/CFT correspondence, which explicitly demonstrates a holographic universe in certain contexts, experimental proof remains elusive. So why does this matter? If the holographic principle holds, it could unify quantum mechanics and general relativity, two theories that currently refuse to play nice. It might also answer lingering questions about black holes, quantum gravity, and even the nature of consciousness. For now, it's a tantalizing what if that pushes the boundaries of human understanding. As we wrap up our journey through these 30 weird and wonderful space facts, remember, the universe is far stranger than fiction. From singing black holes to holographic realities, every discovery peels back another layer of the cosmic mystery. So keep looking up, because who knows what other secrets the cosmos is waiting to reveal. Thanks for joining me on this adventure. If you enjoyed diving into the unknown, don't forget to like, subscribe, and hit that notification bell for more mind-expanding content. Until next time, stay curious. And with that, we've reached the end of our cosmic journey through 30 of the most astonishing, head-scratching, and downright incredible facts about space exploration. From astronauts growing taller in zero gravity to a diamond planet worth more than all the wealth on Earth, the universe never fails to surprise us. Who could forget the moon's gunpowder scent, the silent void of space, or the fact that Venus spins backward while Uranus rolls like a drunken barrel? And let's not overlook the holographic universe theory, proof that reality might just be the ultimate magic trick. What was your favorite mind bender? Did the singing black hole send chills down your spine, or were you more captivated by Saturn's disappearing rings? Drop your top pick in the comments. I'd love to hear which cosmic wonder stuck with you the most. This is just the beginning, though. The cosmos is packed with even more mysteries waiting to be uncovered, from rogue planets drifting alone in the darkness to the possibility of parallel universes. If you're as obsessed with space's secrets as I am, make sure to hit that subscribe button and ring the notification bell. There's so much more to explore, and I'll be here to guide you through every bizarre, beautiful discovery. Until next time, keep gazing upward and questioning everything. The universe is weird, wonderful, and far from done surprising us. See you among the stars.